Hello everyone, I am Dustin Mallett. I am a Master's Electrical Engineering student here in the EDGE program. And I'm just going to go over our simulation, what it looks like, what the simulation framework, the OMNeT simulation framework looks like. To start, I'll talk about OMNeT. It's a commonly used open source network simulator that we chose to use for this project. There is a lot of pretty thorough documentation and plenty of examples that made us decide to choose it over some of the other options that we had available. So each simulation is built up using a network or .NET file and the .ini file that simulates the events that happen in the network. So the networks are put together using connections and submodules that can be used to model all layers of the OSI model, from the physical layer and power consumption to the application layer. This example, this is the networks .NET file in the local area networks folder. This is broken up into smaller different networks here, the two hosts, the switch LAN. And we can see that each one has hosts, hubs, switches, and buses. We can open and edit any of these. And see, so these hosts have submodules in them as well, which includes these client and server applications and message dispatcher. All these have a source code, which we can see here, that can be edited to fit in any application needed. So these submodules just build onto each other, putting one submodule into the next, so we get this network that we can build up. So for our project, we are simulating TCP congestion control in a data center. As Eric has already shown, this is made up of a group of servers all connected to 3 layers of switches in a tree topology. Our simulation has the top layer of the switches connected to the internet, where a number of clients are connected and request data packets. Right now, our most recent iteration just has the 1 layer of switches, while we work on getting some better results. Right now our simulations have been airing out after a certain point due to the queues overflowing. But if we go in here, we can look at the source code. We further define the network and how these submodules interact with each other here. So you can drag and drop the modules into the this designs part of the .NET file. And that will, or you can also code them this way, but dragging and dropping them will add the different lines of code here. We can further define how these interact with each other. So we start with the basics from the .NET file, and then we add on to it. So Eric has altered the source code of our network here to allow us to put as many servers, clients, or switches here as we want as a variable. So this allows us to have a lot more flexibility with our simulations, as we don't have to draw out a tree that goes from layer of switch to a layer of switches to a layer of switches to 128 different servers, which would be individual objects. And there's no need to make any significant changes as we go back and forth between configurations if we just put this number of switches here as a variable. Now I'll just quickly touch on how we've built our simulation up. So we've made some significant strides since we started making progress as we tackle this learning curve. The first step was just running a simulation with, let's take a look at it here. We're going to have, we did 2 hosts to a bus, or 2 clients to a bus to a switch to 4 servers. So this is the first one that we ran. We've continued to build up to it. This one has no internet. They're all directly connected. And this was one of the simpler networks that we could use related to what we were trying to do, where we have a number of hosts tied to a switch, tied to a number of servers. So this was actually the first iteration of this that we used to simulate, to try simulating, and we've continued to build onto it. Now, to just skip ahead from our first version to our fourth version, we went from this 2 hosts, 1 switch to 4 servers, to this where we have our host clients tied to the internet. These in turn are tied to the level 3, level 2, level 1 switches, where we can define the number of switches, and then those go to the servers, where we can also define the number of servers. So this, with just changing the variables here, we're actually able to match the network that they show in the paper. And then the next part we have is the actual different algorithms that they perform in that paper. Now we'll just dive into the simulation. So here I am in the datacenter.ini. Right now we have a network that's similar to that of the paper. So we're going to try to change the congestion control algorithm in the data center. So if we look here, right now our TCP algorithm class is TCP Reno. We can actually just change this here so that there is no congestion control. We can change it to TCP Reno, TCP Tahoe, TCP Vegas, TCP New Reno, so a handful of others, and then evaluate how those, how they impact the throughput against each other. So now we have the TCP Reno, and I'm just going to go ahead and run the simulation that we have at this point. Here is the simulation file that we have. You can see the simulation will run here. We'll get our, all the events will be logged here on this side. This is from a previous simulation. Now we can just hit run here and we can see a little bit about what it shows. Just going to step through all these events. Client sending requests to the internet, through to the servers, and getting replies. This one right now we just have 5 clients to 1 server. We've been having some errors when we have too many servers where our queues overflow and then our simulation just ends. So here's this. So this one ran all the way until it's done, and then we can get the results from that, which I'll talk about a little bit. So we are able to pull a lot of vector data here, and then we can graph it within OMNeT. So now, just to wrap up, I'll talk about where we are and what comes next for our team. We have TCP congestion control algorithms and a network to work with. We're able to simulate and get results that show throughput is lowest for no congestion control and goes up at different levels for different algorithms. We're trying to show that the throughput values against requests per second, such as what's shown in the paper, so throughput to requests per second instead of just throughput against time, like we have now, and we want to show how each algorithm sort of has its own bottleneck that it hits, that it doesn't matter how many requests are coming in, the throughput hits a maximum point where you can't go any higher. The data visuals in the paper show that, and so we'd like to show that also. Right now the throughput per time doesn't quite have the same effect. So we're working with different ways to look at the data to show that we have similar results to the paper, even if we use different algorithms. After these, we'd like to work to better randomize which servers send requests and when. and try to work to implement the algorithms so that they're more similar to the algorithms that are in the paper. Working through some of these kinks will give us a really solid simulation to be able to demo, where hopefully we can just continue to improve on what we have and just make it better.